All right, so welcome back, everyone. So today it's my pleasure to welcome Cristina Cipriani, who will be talking about a new field, the optimal control approach for the training of NeurODEs and the Autoencoders. ODEs. Yeah, thank you, Cristina.
Thank you. Thank you for the introduction, and thank you for inviting me here. I'm very happy to present my work. My talk today is based on two projects that I've been working on during my PhD, two papers. The first one was co-authored by Benoît Monet, Massimo Fornasier, my PhD supervisor, and Wei Wang. And it focuses mainly on NeurODEs, while the second work that I've been doing together with my supervisor and Alessandro Scagliotti focuses on Autoencoders, what we call Autoencoders. So let me show you an outline of my talk today. So first of all, I will start by defining what NeurODEs are and how they are connected with optimal control theory. Then I will discuss about Autoencoders, and in the third part, I will talk about the optimal control problem and how we tackle it. In particular, I will talk about a mean field optimal control problem. And finally, I will show you some numerics. All right, so let's dive in. Let's start with NeurODEs. And since we are talking about machine learning, let's start talking about a supervised learning task. So I guess that you are all already familiar with what a supervised learning is, but let me just recall it here. So the key ingredients are a data set of n training samples, and each training sample is a couple of some future vector xi in the input space and some label yi in the output space. Now, once we have defined a loss function, the goal in supervised learning is to find some function n that goes from the input space to the output space, such that the loss is minimal for all the training samples. And usually what is done is to use feed-forward artificial neural networks to do so. So feed-forward artificial neural networks are the composition of this function sigma, where sigma is a scalar activation function which acts component-wisely on its input. And the input, so the input of the layer is what I call here x0, the vector of the input space, which is multiplied by a weight matrix, W, and it's summed to a bias vector here. And this is repeated for all the number of layers. So this is like the typical structure of deep neural networks. And the goal is the structure of the function is fixed, and what we want to find is these weight matrices and bias vector such that the output of the layer, which I call X capital L, because L is the total number of layers, is close to the corresponding label. In particular, from now on, let me use the following notation. So I will denote with F the function sigma applied to its input, and I will denote with theta all the trainable parameters of the network, so all the weights and all the biases. So instead of having this function sigma, I will have F. And now the neural network, the feed-forward neural network, can be described as, again, the composition of this function phi, L times, where every function phi at every layer is equal to the function F. Now, this is how deep neural networks are usually defined, feed-forward deep neural networks. However, people realize that it has been, in some cases, especially when the number of nodes, so the dimension of these intermediate layers is constant, it is beneficial to modify the structure of the networks, and so to add an identity. So these new types of neural networks have been introduced from practical considerations. So people realize that it's good to use neural networks where, again, we have this composition of these function phi's, but now the function phi is not only equal to F, but the output to F is also added to its input. And so this kind of connection is called skip connection or residual connection. And this kind of architecture, this kind of deep neural networks are called residual neural networks. Now, as I said already, these kind of neural networks have been introduced empirically from practical considerations. However, they have turned out to be very interesting from a mathematical perspective, because if we look at every layer of these ResNets, this looks like an explicit Euler discretization of an ODE, a dynamical system which is controlled by some parameter theta. And in particular, this continuous version of these networks are called NeurODEs or neural ODEs. And this observation bridges the world of machine learning and residual neural networks with the world of optimal control theory. And the idea of my talk and many other works is to use techniques coming from the well-established world of optimal control theory and try to apply to the world of machine learning that is still full of unknowns. Let me elaborate a bit more about the distinction between residual neural networks and control systems. So, as I said already, residual neural networks have layers. So we have a discrete version of the control system, where in the control system we have a continuous interval, which is usually closed, compact, from 0 to, let's say, capital T. And then the key ingredient of residual neural networks is this layer function. So the fact is phi L that I defined before, where we are summing the input to the layer plus the activation function. This is what I call layer function applied to the input. While on the level of control systems, we have an ODE controlled by some parameter theta t. Now, another distinction lies on the definition of the parameter. So, in the case of ResNets, the parameters are vectors, let's say in dimension Rm, while in the case of control systems, we need to assume some Lebesgue regularity. So we'll have these parameters at every time in the interval will have to be L2 or L infinity. And then, of course, in the case of ResNets, we have many layers for the network. And so we are interested in the composition of this function phi, and we are interested at what happens at the final layer, because that's where we measure the mismatch between the output of the network and the label. In the case of control systems, then if we have such an ODE, this is a non-autonomous ODE, so we can define a flow. And what we are interested in as well is the flow at the final time. So what happens when t is equal to capital T. And there are many consequences of this parallelism. So first of all, we can study the expressivity of neural networks as a controllability problem. So we can use techniques in this world of controllability, and we can ask ourselves, okay, what kind of functions can we express with these neural networks? Or what can our system reach? And secondly, we can interpret the training of this neural network as an optimal control problem. And that's actually what I'm going to focus on in my talk today, and what I've been focusing on during my PhD. So how can we interpret the training as an optimal control problem, and what are the advantages of such an interpretation? Can we maybe use ways of solving optimal control problems from the theory in order to devise, for example, new training algorithms? So this is the goal of today's talk. But first, let me explain what is an optimal control problem and how it arises. So as I said, a key ingredient of supervised learning is a labeled data set. So we have n data, which are the couplings of the vectors and the labels. As in the machine learning world, we need to fix the number of layers. So this would be the depth of the network, or in the continuous time version, capital T of the time interval. And then what our goal is to learn parameters theta t in such a way that for every datum in the data set, the output of the network, which is x capital T, so at the final time, is close to the corresponding label y0 for the datum I. And so this can be written as an optimal control problem, because our goal is to minimize some function j. This function j is an average, a normalized sum over all the data in the data set of some function L. Now, this function L appearing here can be decided based on the application. So, for example, we take as a, typically we take this L2 norm, and because this function L aims to measure the distance between the output and the label. And now this is how a normal loss function looks like for a machine learning problem. And how can this be interpreted as an optimal control problem? So the thing is that we do not only care about minimizing this cost function j, but the difference is that also we know how this datum xit is evolving through the network. And so we know that xit satisfies the following ODEs, this neural ODE that I showed you before, starting from the corresponding initial datum. And so this is why we can interpret the training as an optimal control problem. And in particular, what we will study is the regularized problem. So we will sum an L2 regularization here, and we will have some parameter lambda that is multiplied in front. This is actually very important to have. So this is not actually people started to have L2 regularization in machine learning, and then that they realized that it's not needed to have a regularization in the loss in order to obtain good results. So you can also work without lambda, with lambda equal to 0. But for the theory, it's very good to have some regularization. So this will actually be very important in our theory. And we also, in the second work we did, we focus on what happens when lambda is equal to 0. So when we are really doing what machine learning practitioners do. So this is the optimal control problem. And of course, the goal also, if you're familiar with the world of optimal control theory, you will know that one of the most important tools is the Pontryagin Maximum Principle, which gives a set of necessary conditions for a minimizer. And we will try to use the same or to derive the same in our case. But before doing that, let me also discuss what are these Autoencoders that I mentioned in the title. So as I explained to you, these NeurODEs comes from practice, from people who decided to add these skip connections in the networks. However, these residual neural networks, or this layer continuous version NeurODEs, have a limitation. The limitation is that in order to make sense of this sum here, we need that at every layer, the width of the network, so the dimensionality of the layer, or you can call it also number of nodes per layer, remain constant. So, and then these residual neural networks, or NeurODEs, will always have this rectangular shape. However, in machine learning, it has proven to be very useful to have neural networks in which the dimensionality of the layers changes, and there are changes of the width. So, for example, very important and famous example of such networks are autoencoders. Autoencoders have a very specific structure. So let's say that we have an input vector of this dimension. First, the network has a first encoding structure. So this first part of the network is called encoder. And the objective here is to decrease the dimensionality of the input data till a certain dimensionality that is chosen a priori from the user. Then this dimensionality is kept constant in the bottleneck. And then in the decoding phase, in the decoder, the dimensionality is increased back. So you can see that number of nodes changes. And the goal is to have an output that has the same dimensionality as the input. And these kind of networks have shown to be very useful for reconstructing data, for example, and also for dimensionality reduction. That is because if we start from an input and we are able to completely and accurately reconstruct it, then that means that we are able to represent the input data in a lower dimensional space. And we can then analyze the data in this lower dimensional space rather than the big original one. That is, these kind of networks are very much used in practice. And so what we wondered is, can we somehow extend this NeurODE model to the case of neural networks with varying width? How can we make sense of these skip connections when the dimensionality changes? So we tried actually many ways. We tried techniques from viability theory. We also realized that there are a certain type of ODEs in which the dimensionality can change. However, we came up with another solution, with actually a very intuitive one. So what we did is we embedded our autoencoder structure that we want to study into a higher dimensional ResNet kind of structure. And then what we want to do is to write an ODE that describe this autoencoder in here. So essentially what we did is to take some components, these are the ones depicted in green, and do not take them into consideration in the evolution of the ODE. So how did we do that? Let me be a bit more formal. And let me focus on the encoding phase. Let's say that we start with an initial datum X that is in dimension D. Then the way that we model this autoencoder is by using two filtrations. So we have a set of indices of inactive components and a set of indices of active components. So at the layer 0, when we have the initial datum, of course, the inactive components are the empty set. All of the components are active, as you can see here. And the active components are all of them, so from 1 to D. And then we slowly increase actually the size of the sets of inactive components, and we decrease the size of the sets of active components. Now, these two sets give partitions of 1 to D, and they are very useful because we are able to obtain a ODE that describes the evolution of the data through the autoencoder. So let's say that is because we have that for the inactive components, we don't care about them. We don't want them to be part of the evolution anymore, these green dots. So essentially we say that the time derivative of the inactive components is equal to 0. They just remain constant and we don't look at them anymore. While the time derivative of the active components is equal to the same function f that I defined earlier, which is the layer function. And of course, this function only takes as input the active components of the previous layer. And so we can make sense of this sum of this skip connection in this case. This kind of model can also be extended to the case of to the decoder, because so far I've only described the encoding phase. However, we need to be careful, because when we, let's say we turn an inactive component into a active components, we cannot simply use the value that was in the previous layer here, because the value of this node here will not be equal to 0, but it will be constant to the value of this node here. And so we don't want to be biased by the previous value, constant value. And that's why I didn't present the decoder, because the notation gets a bit more involved, and I didn't want to get into details, but the idea is the same, and we will have again 2 filtrations of inactive and active components. Now, let me also mention something that is very important to notice right away. That is that this kind of dynamic will be highly discontinuous in time, so in the layers. That is because at certain layer, there will be sudden drops of dimensionality, and components that were active before will become inactive. So this is something very interesting to keep in mind for the theory. Now that we have been able to describe both residual neural networks and autoencoders with these ODEs, then we can talk about mean field optimal control theory, because now we can interpret the training of these networks as an optimal control problem, and we can try to tackle this problem using techniques coming from optimal control theory. In particular, a lot of people already worked in this field and tried to use techniques of optimal control theory. So what we did was to study the mean field version of this optimal control problem that I will define now. So the idea is that we are interested in the case where the initial data of the network is a distribution. So it's as if the number of data of the data set goes to infinity. So in this case, we want to see what if we can study the problem when we have, instead of having n initial data, we have a distribution of initial data. And then if we are able to study the problem, then we will obtain results that are also related with the generalization capabilities of our network. So let me first tell you how the mean field optimal control problem looks like. So let's say that we have the initial data x0 and y0, which is distributed according to a distribution mu0. Then we know how x0 and y0 are evolving through the network, right? Both the NeurODEs and AutoencodEs. We know that the feature vectors will evolve according to this ODE, which depends on time, and the labels will not evolve. That is because whenever the data is passing through the network, the label is not influenced, and the label will stay constant. And so its time derivative will be equal to 0. Now, if we denote the law of xt and yt at time t or layer t by mu t, then according to well-known results of mean field theory, mu t satisfies the following PDE. So now, instead of having n ODEs for every initial data, now we have a unique PDE that describes how the entire distribution of the data is flowing through the network. And so we are able to write the mean field optimal control problem. So once again, we want to minimize some function j. And the function j actually looks the same as before. So before we had the sum over all the data. Now this is an integral, and before we were measuring the mismatch through this function L between the output and the label. Now we are doing the same, so we are taking the integral of the function L evaluated at mu t, because mu t is the distribution at the final layer. And then we have, once again, the regularization term, which looks exactly the same as before. Now, of course, it's an optimal control problem, so we have an additional constraint, we have additional knowledge, so we know how this mu t evolves, and we know that it comes from the following PDE. So instead of having n constraints for every ODE, now we have a unique PDE. And so first of all, we wrote down this mean field problem, and then we thought, okay, let's now try to derive a mean field version of the Pontryagin Maximum Principle. So as I said already before, the PNP gives a set of necessary conditions. So similarly, we obtain here a set of optimality conditions. So we obtain what we call our mean field Pontryagin Maximum Principle. So we know that if theta star is an optimal solution of the problem, then theta star will satisfy the following equation. So of course, this is you can see the typical structure of the PNP. So we have a forward dynamics, backward dynamics, and then an optimality condition. So the forward dynamics is simply the PDE that I showed you before, the constraint here, which will hold also for the optimal one. Then there will be a backward dynamics, and that is backward because we know the value of this function psi at the final layer, and then it will be back propagated through this PDE. And then we have an optimality condition, which is somehow, it's related with the typical maximization condition of the Pontryagin Maximum Principle. Now, one of the contributions of our first paper is that we derive this mean field Pontryagin Maximum Principle in terms of the Lagrange multiplier theorem. That is because we wanted to explain this theorem, this very important theorem, in such a way that it would be understandable also for machine learning practitioners. So that is the Lagrange multiplier theorem. And that's how we actually obtain this set of necessary conditions. Let me now draw a comparison about our first work and the second one. So in the first work from 2022, we prove that under certain regularity assumptions on this layer function f and convexity assumptions on the objective function j, then we have some very nice property. So we obtain that this mean field Pontryagin Maximum Principle that I showed you before is not only a necessary condition, but it is also sufficient. And so we can get inspired by these first order optimality conditions, and we can use it for the numerics by starting with an initial guess for theta and then solve multiple times this system of equations. But we will discuss this later on. Just the important thing that you should remember from this part is that by having nice assumptions on the function and f and j, in particular this convexity assumption, then we have also this sufficiency. Moreover, we have that the optimal control theta star is unique and it's Lipschitz continuous, and it depends continuously on the initial datum, which is a very good thing because then we can talk about the generalization error. So let's say that in general, we are in the mean field case, so we assume that we know the true distribution of the data mu0. But what happens in practice is that we don't know the true distribution. What we know is that we have a data set, right, with n data. So this is an approximating empirical measure, mu0n, made of the data set. And now, since this solution, this optimal control theta, depends continuously from the initial distribution, then we can denote with theta star the optimal solution obtained starting from mu0, and theta n, the optimal solution obtained starting from this approximating measure mu0n, and then we are able to bound this error, so this generalization error, how well we do with the approximating with the solution that we obtain from a data set in comparison with the true solution by this term on the right-hand side, which is a constant multiplied by the Wasserstein-1 distance between mu0 and mu0n. So essentially, this means that if we are good at approximating the true distribution mu0, then we can obtain a good generalization error. Now, this is what we obtain in our first work, and then we wondered, can we extend the results to the case of width-varying neural networks? So these autoencoders that I showed you before. And of course, in the way that we model these autoencodes, then we need to assume that we have something that cannot be, that this function, layer function f, cannot be continuous in time. So we realize, okay, we have to change this assumption. Moreover, once we are changing the assumption, then we ask ourselves, can we prove something for the case of unbounded layer function f? That's because in our first work, we took as prototype for this layer function or activation function, the hyperbolic tangent. However, this is a very nice function, and many people in machine learning actually use functions such as the ReLU function or the leaky ReLU, which is not bounded in theta. And so we said, okay, while we are there, let's change all of the assumptions on our function f. And then we also wondered about the convexity assumption on the cost functional. So, and in particular, we realized that the function j turns out to be convex, when the parameter lambda is large enough. And that's why I told you before that this regularization lambda is this term in the cost function that is multiplying the regularization term. So we realize that in practice, people don't really need to have regularization in order to have to be able to train the network. And so we said, okay, let's try to put this lambda equal to 0. So we lose convexity. So in that second work of ours from 2023, we relaxed this assumption. So we assume just measurability in time instead of continuity. We assume some linear growth in theta, which is okay because the ReLU has a linear growth. And then we completely dropped this convexity assumption on J. And of course, the results don't look as well as good as before. So now the mean field Pontryagin maximum principle is only a necessary condition. So we need to first know that that theta star is optimal before we are able to use this system. But this is quite normal because the Pontryagin maximum principle becomes a sufficient condition whenever the cost function is convex. Now, since we dropped these convexity assumptions, we also lost the sufficient part. Moreover, by dropping this assumption, we also lost the uniqueness of the optimal control. And by losing the continuity in time, we also lost the Lipschitz continuity of the optimal control. However, the good news is that we are still able to obtain a generalization error. So once again, we denote with theta star the solution obtained starting from mu0, theta n, the one obtained with mu0 n, and then we obtained the same kind of bound with this constant c that multiplies the Wasserstein-1 distance when we add these assumptions that our cost function will not have a global minimum anymore, but we might have many local minima because we're not convex anymore. But we assume that around these local minima, the loss is convex, which is a reasonable assumption. And so, yes, we are able to model and analyze, obtain some results also for the case of width-varying networks, such as the Autoencoders that I showed you before. We are able to consider ReLU and leaky ReLU. In particular, let me be precise, we always need some smoothness on this layer function. So these would be smooth versions of the ReLU and leaky ReLU. And moreover, we are also able to consider a non-convex cost. Of course, if lambda is large enough, then we obtain back all the nice results that we had before, but we are still able to obtain most of the results also in the case of non-convex cost. So now in the...
Sorry, so there was a question in the chat.
Oh, right. The control slide 21, yes, in time. So Goncalo, this is, sorry for missing your question before. Yes, it's continues with respect to time. That is what we obtained. So if there are no further questions, then I would go ahead with the part about the numerics. So I want to conclude with some numerical experiments. All right, I don't see any question in the chat, so I can go ahead. So I showed you before this mean field Pontryagin Maximum Principle. And now I want to show you the algorithm that we devised starting from it. So let's say that we are in the convex regime, so that we know that this lambda parameter is large enough. Then what we can do, as I already hinted before, we can, since we know it's also a sufficient condition, we can start with some theta 0, with some guess, random guess, and then we repeat until converges this system. So what we do is start with theta 0, we solve the forward PDE, we solve the backward one, and then we use the third equation to update the optimal control. And then once we update the control, we go back to the first step and we continue this. Now, of course, the first question here is, okay, you repeat until convergence, but how long do you need? How many iterations do you need? And well, what we proved in the convex regime, when lambda is large enough, we obtain that this here is a contraction, thanks to lambda being large enough. And so actually in a smaller number of iterations, we are able, thanks to the fact that this is a contraction, we are able to converge to the right solution. And indeed, we perform numerical examples in the convex regime, and we really see that we can train the networks in low dimension with let's say 10 repetitions of this number of iterations. But it's not really easy to set this parameter lambda. So we realize that this parameter lambda depends on a lot of factors, depends on the support of the initial distribution, depends on the dimensionality of the data. And so if we increase the dimensionality of the data, it becomes very complicated to set this parameter lambda large enough, because we want it to be large enough in order to have convexity, but we don't want it to be too large. Otherwise, you know, since this lambda is multiplied the regularization term in the cost function, If lambda is too large, then the minimization will focus on the regularization and not in the error part, in the part where we are actually performing the supervised task. And that's why we realize that we need to study the non-convex regime. So we need to consider the case when lambda is not sufficiently large to obtain a convex function, and it might even be equal to 0. That is what happens in practice. So I will just finish now the convex part, and then I will answer to the question. Yes. So in the non-convex regime, what we found out is like, I will not go into the details. I did not go into the details, but what we found out is that we got inspired by the minimizing movement schemes of gradient flows. And what we did, we added this term in this equation for the update of the parameter, and by adding this term that's making sure that we are not going too far from the previous guess, then we are able to obtain a contraction here, even if lambda is equal to 0, or even if lambda is not large enough. Now I will check the question. Could you comment on if the forward dynamics of mu t is some type of Fokker-Planck equation? Yes, I would say that this is a transport equation where the transport depends on this function f. And so it entirely depends on this. I hope this answers your question. Okay, thank you. So thank you for the question, because then we can talk about the PDE, right? Because I told you now that everything looks nice in the convex regime, and we can make it work even in the non-convex regime by adding this term. However, there is still the issue that here, what we want to solve are PDEs. So actually, if we perform numerical experiments, we have to consider data in very low dimension. And indeed, this is what we did in our first paper. So in the first paper, we focused on the convex regime, and we consider like classification task in a one-dimensional domain or two-dimensional domain. And we studied, we really solved these PDEs that are appearing in the mean field Pontryagin Maximum Principle. And what we did was to try to numerically solve these PDEs with different methods. So for example, we tried with a particle method, with Monte Carlo, or finite volume method. And then we compared the solutions. So the theta, this is the plot of the thetas, obtained the parameters obtained with different methods in 1D. And what we realized that actually the most convenient thing is to use a particle method. Particle method means that we are sampling some particles from the initial distribution mu0, and then we let evolve just these particles according to the ODE instead of the PDE. Of course, this goes in, it's a step backward with respect to what I told you before, that we are interested in a mean field version of the problem. However, this is just this just comes from numerical reasoning, because in numerics, if we want to try to apply our algorithm to high-dimensional cases, then we cannot solve this PDE. And so it's more convenient to just go back to the case of optimal control theory. However, it's still interesting to have consider this mean field version in the theory, because all the bounds that we obtain are independent from the number of particles. And that's why this mean field setting is interesting. So now that I explain you what to do in the case of non-convex functions and in the case of very high dimensional data, let's talk about a real machine learning task. So a reconstruction task on images of the MNIST dataset. So the MNIST dataset contains images of digits. This is a very famous dataset, and these images have dimension 784. And what we did is to test our AutoencodEs. That is because I told you that this AutoencodEs was born by our desire of describing autoencoders with an ODE. However, we changed autoencoders because we added these skip connections in between layers in the active components. So we wanted to test how these kind of autoencodees would perform on a real task on the MNIST dataset. So what we did is to build such an autoencodee. As you can see here, I used the green for the inactive components, as before I used the green for those nodes that would just not be part of the dynamics anymore. And then we made some drops of dimensionality. So from dimension 784, we decreased it to dimension of 512 of active components up to the bottleneck where we consider vectors of dimension 32. So usually in machine learning, these numbers are decided a priori. And that's actually what we did. We checked how people reconstruct MNIST images, and we found out that this is a typical structure of an autoencoder. And so we kept it the same with our skip connections. And what we tried to do was, given a data set, given its input here, to reconstruct exactly, to obtain exactly the same digit. And this, in here, you can see the reconstruction of our digits. So this is like this column and these columns are the original images. And here in this column and this column, you can see the reconstruction. Of course, it doesn't work perfectly. This is the code still needs some changing. However, our goal was not to devise a new way of reconstructing images. We are mathematicians, so what we wanted to do was to analyze the problem and maybe and just have this reconstruction as a proof of concept that such an autoencoder could work for reconstructing the images. And then what we did was to study this autoencoder. So we noticed something very interesting that is probably related with the implicit bias of neural networks. So what we realized is that when we start with an initial guess of only zeros, so all these parameters theta are set to 0 at the beginning, and then we use our mean field Pontryagin Maximum Principle to train the network, this autoencodees with skip connections, then there is a very interesting behavior. So as I told you, in the bottleneck, we set this, it's called latent dimension, to 32. However, when we look at the vectors in the bottleneck, we see that these vectors are actually sparse vector, which with consistent support. So we realize that out of this dimension 32, only 13 components are non-zero, and all the other ones are equal to 0. And what is very interesting is that, first of all, the support is the same. So for all the numbers in the data set, it's always the same components that are non-zero. And moreover, we also realize that it makes sense to also consider this latent representation of the data, because, for example, if we look at the number 4s, these are depicted in blue in this picture, and a digit of number 9, of course, if the digits look very similar to one another, as you can see here, the 4 and the 9, and also in the latent representation inside this bottleneck, you can see that these vectors look very similar, and the same happens for similar numbers. So we're really able to obtain a representation that makes sense. Moreover, we realize that this phenomenon that only 13 components are non-zero actually has a meaning, because we realize afterwards that the MNIST dataset despite being in dimension 800, actually has a true dimensionality that people estimated to be around 13. So it seems like our autoencode trained with our network is able to detect the true dimensionality of the data set. And what we did is also we compared it with the...
Sorry, I have a question.
Yes.
It's the sparsity you observe in the MNIST data set. Do you think it has anything to do with the regularization term you have in the autoencoder?
It's possible. So actually, we don't know what is giving us this nice behavior, because we don't know if it's about the training method, the regularization, or this autoencode structure. What we did, we compared it. This is what I was going to say, with autoencoders, with these standard autoencoders. And as you can see here, if I start with a standard autoencoder and I set all the parameters to 0, it will not work well. So it will actually, in the latent dimension, it will learn some representation, and it will learn a representation that is a mean representation that is not really informing. And if I train an autoencoder with a Gaussian when the initial guess is normally distributed with very small variance, then I obtain something that is the orange line here with this variance, which is non-sparse. So this sparsity that we obtain in our experiments seems to be happening only with our autoencode, but we have no idea why this is happening. So we are still studying this phenomenon.
Sorry, one more question.
Yes.
The regularization term, like, do you change it during this process, or is it fixed at one value?
It's fixed.
Maybe if you want, you can check if you change it, whether you're going to see the same behavior, whether it's always starting non-zero components. It could be because
So you think that if we change it, so after some, let's say some epochs, then we change this regularization parameter and we will be able to obtain sparse vectors?
I think you might get a different number of sparse vectors.
In our autoencodes or in standard autoencoders? Because
in your autoencodes, I mean.
Autoencodes, okay. Yeah, that's something that we didn't try. Yeah, it's interesting.
I mean, that's what essentially regularization does. It tries to specify your output in some way by forcing all of the other components to 0 or close to 0.
I mean, that's what L1 regularization would do, to sparsify the controls.
Yeah, even L2 does it, but it does it softly instead of hardly.
Yes.
Yeah. Thank you.
Thank you. And I think there was another question.
Yeah, this Manico here. This reminds me of kind of like dictionary learning, okay, and corresponding sparse coding. So it'll be interesting to visualize each of the learned, it's not a basis, but the learned atom or factors. Because the dictionary learning always have difficulty of, well, not difficulty, but the semi lack of good theory about how to populate the initial table, a dictionary of atoms, right? So if you can find it automatically by zero initialization, that is very, that is actually quite intriguing. Very, yeah. So.
Yes, that's what we also have another project with the same co-author of this one about dictionary learning, actually. So we are trying somehow to double check our results here and try to use these results for dictionary learning. But yes, thank you. That's a very good point. And you got it.
Because I worked with KSED, another kind of problem before, and on the earlier comment, the L2 versus L1, that's also a technique used in dictionary learning or compressive sensing.
Yes.
Which is that you start with L2, kind of a soft, but not very strong, and then gradually increase it to make it more L1-ish, But that's called, I think it's called fixed point continuation. I actually forgot. But so those idea is also used in ridge regression, which you might already are familiar with. It's also related to the smoothness of your underlying function space you're trying to use to do your representation. Anyway, very interesting. Thanks. Yeah.
Okay. Thank you. Thank you.
Yes, so maybe you can continue your talk and then you can answer the questions.
Okay. Okay. I will just remember that there is another question in the chat, and I will continue.
I will remind you. Yeah.
Thank you. And I will continue with the next one. Essentially, yes, that's that. What I've been showing you so far is that the interaction between machine learning and optimal control theory. So try to use optimal control theory to better understand machine learning, and try to use it, for example, to create new type of architectures, as this one with the skip connections. And we also wondered, can we use additional knowledge on this additional knowledge in order to understand how to build this network, because that's always a bit unknown, how to build a network. So how to decrease dimensionality, how many layers we need, and so on. And so what we thought is that we can relate this idea with the discretization of ODEs. So in the ODE that I showed you at the very beginning of my presentation, in these ResNets, we have a discretization, explicit Euler discretization of an ODE, right? With a unitary step size. However, if we are studying the continuous time version, the ODE, and we want to discretize it, then very often in these neural ODEs, there is also a step size, a residual step size that is multiplied in front of the layer function. Now, since we know that the way that we usually discretize ODEs is that we want to pick a step size that is consistent, that it's always smaller and the inverse of the Lipschitz constant of the function on the right-hand side of the ODE. So we thought, okay, can we maybe use this to build a network? So of course, we don't know the Lipschitz constant of the function of the ODE because it depends on the parameters, on the trainable parameters. However, we said maybe we can do a sanity check starting. So once we have trained the network and we know the optimal controls, the parameters, then we can compare the we can do this sanity check, posterior one. We can plot the inverse of the Lipschitz function for every layer. This will change because theta will change at every layer. And we can compare it with the residual discretization, the t. Of course, the t will be constant because we will not change the t in the ODE at this point. And so if we compare this inverse of the Lipschitz constant and the t, we want to see that the t is always smaller than the inverse of the Lipschitz constant. However, the first time we tried this sanity check, we realized that this was not the case. As you can see here, the inverse of Lips becomes smaller than the discretization. And actually that helped us because we realized that there was a problem, that I made a mistake when coding the network, and that actually there was a too big increase of dimensionality at the final layer, and I had forgotten an intermediate one, let's say. And so this was a wrong autoencoder that was, so I corrected it. And this helped me to create an autoencoder in which the inverse of the Lipschitz constant is always higher than the discretization, the residual step size. And so we think that this knowledge can also help us to decide how to build this autoencoder. So we are not obliged to have a symmetric structure. And actually, by looking at the behavior of the Lipschitz constant after training, we realize that the Lipschitz constant or the inverse of the Lipschitz constant is always higher for the encoder than for the decoder, which means that during the decoding phase, our Lipschitz constant will be bigger, and we will need more efforts in order to decode back the vector into the original image. And so we see that it's possible that we can drop some layers in the encoder in order to focus, let's say, our strength in the decoding phase. And so this is still an open idea that we have and that we will work on how to build these networks based on this knowledge. And with this, I would like to thank you for your attention, and I'm happy to answer your questions.
Yeah, thank you very much. So there was this question on the chat by Roussel. Roussel, do you want to? Okay, you are here. Yeah, you can talk. Yeah.
Yes, thank you for the talk. So yes, the first question was more about the true dimensionality of MNIST. You mentioned the number 13. I wondered if you could elaborate a bit more about that, but I have a few more questions, so if that one's not that important, you can skip it.
Okay, so we actually did not know about the true dimensionality, and I think there is no theory related to the true dimensionality of the MNIST. There are just multiple empirical ways to calculate this, what people call the true dimensionality. So we realized then that I don't remember exactly. There is there are multiple references, but I don't remember exactly how they calculate the true dimensionality of MNIST, but it's always an empirical method, and it's always an upper bound.
Okay, thank you. Thank you then. I'll check more on that, but I wanted to ask another one concerning the other view on your ODEs, because beyond the view that these are just continuous depth ResNets, we can also view them as universal differential universal ODEs, like I guess the loss function incorporates every single steps in the trajectory, not just the final time step, right? We are just trying to actually approximate an ODE, and we're not just interested in the final.
Yes.
So I wonder if your results apply to that kind of view.
So we focused our theory to the case where we are only interested at what happens at the end. I mean, of course, what happens in between is somehow it's part of it. It's part of this, for example, this mean field Pontryagin Maximum Principle, because as you can see, it's one of the necessary conditions. So here, this is in the case of the PDE, it's the PDE that describes the forward movement. So I'm not so sure, because I'm not too familiar with what you call the universal ODE. But yeah, I think I would have to think about this, but I think we mainly focus about what happens at the final layer.
Okay,
but use what happens before, of course. Yes, sorry.
Well, thank you very much. I think it's good that you even mentioned the slide, because I was wondering on this slide, so you only have the initial, the boundary conditions essentially. And I wonder, the finite volume method, I mean, the particle method you mentioned is very intuitive. I can kind of visualize how you can sample a few points and then just make that flow. But then how do you apply the finite volume method to solve this? It's a bit not clear. Can you please help with that?
So, I mean, the finite volume method, essentially you are taking this initial distribution and then you're discretizing it, right? And then moving every part. Yeah.
Every single point, every single data point.
Yes, but you need to first discretize. So you would discretize the initial distribution U0, and then you would move it according to the this finite volume method, which is different or slightly different from the, now I don't remember the details exactly, but it's slightly different from the particle method, when you simply, instead of discretizing the distribution, let's say that this is the initial distribution. So sorry, it takes a while. Yes, this is the light blue and light green one. So it has two colors because it corresponds to different labels. But then in the finite particle method, you would sample some particles, and in the finite volume, you would really discretize this entire interval here and then move every part.
Okay. I guess I was wondering, how does the data that you have actually come into play? But that's what you call the discretization. Then, okay. Okay, that makes sense. Thank you very much. I think those are the most important questions that I had. Thank you so much for the talk.
Thank you for your questions.
Yeah, all right. Any last questions or comments? All right, seems not. Thank you very much, Cristina, for the nice talk. And yeah, I'll send you an email later. Yeah, thank you.
Okay, thank you very much. And thank you for listening to me.
And thanks for the nice talk. Thank you. Bye-bye. Bye, everyone.
Bye-bye.